Kiran Batchu. Many of us use Google Maps to find directions to places. But if you see the list of stepwise directions, only the first step mentions the true cardinal direction. And by cardinal direction, I mean the words north, south, east, and west. But if you see the rest of the steps, it only uses the words left, right, straight, and U-turn. So why is that? The reason is when we start from a location, the assumption is that we have spent enough time in that location to know which direction is east and west. But as you start driving and you start making turns, it becomes very difficult to keep track of the actual direction that we are driving in. But you can still keep track of it by looking at the north arrow. But that becomes very difficult because we need to focus on driving safely at that time. Also, another reason is that we do not think of location in terms of cardinal directions in our daily lives. We typically think in terms of left of something, right of something, in front of something, or behind something. Now, users typically have strong reactions when they're presented with technical jargon that they are unfamiliar with or cannot make any sense of. And that leads to a lot of frustration, like this user here. Now, can you imagine the spike in road rage incidents if Google Maps starts giving only cardinal directions? The point here is that Google Maps tries to suppress the technical jargon as much as possible and surfaces its natural language equivalents to reduce the cognitive load. And that is why Google Maps is so easy to use. In fact, Google Maps is based on a system called Geographic Information System, or GIS. GIS is a system that creates, stores, analyzes, and visualizes geographic or spatial data. Now, finding directions is a very narrow use case of GIS. GIS can do much more than that. GIS can help you understand how places are connected not only physically, but also qualitatively by merging different kinds of data sets. It helps you visualize how locations and phenomena influence each other across space and time. And it is these hidden connections and deep observations that you derive from it that makes GIS so valuable. And it's no wonder that GIS is being used in almost every industry. But yet, GIS or spatial analysis is not part of the mainstream data analysis. The main reason is technology. The current GIS systems are designed to be used by trained GIS and IT professionals. It involves setting up of map servers, map services, geodatabases, and it needs GIS domain knowledge of map projections, coordinate systems, and specific data formats like shapefiles, GeoJSON, and geopackages. But big organizations have big budgets, so they can hire a team of professionals to set this up. But think of all the small organizations, like small business owners, local newspaper agencies, small city and county governments, and local community organizations. They simply do not have the budget to hire a team, nor they have the bandwidth to learn and set it up themselves. As a result, many of these organizations are unable to use geospatial analysis in their work. So how do we break down these barriers? One of the main ways is to reduce the technical jargon as much as possible and bring the language of analysis as close as possible to the language of thought. What I mean by this is, for a data analysis, you begin by constructing your analytical question in your natural language, which is typically your mother tongue. But then you try to answer that question by using the language of your analytical software. Now, it could mean writing scripts in Python, R, or some other programming language, or it could be just clicking buttons on a UI of a software. Also, another way is to design software architectures that meet where the users are in terms of geospatial skills. Also, we need to create mechanisms that enable us easy sharing of geospatial analysis that are easy to use and easy to understand. Now, in the past few years, there has been improvement in this due to the simultaneous convergence of several new technologies. And this has given rise to what is called modern GIS. Now, today, an average laptop or a desktop is powerful enough to analyze reasonably sized data sets without needing to have special hardware. Also, geospatial analysis tends to be very data heavy. So with cheap cloud object storage, you can organize your geospatial data in the cloud. And since it's in the cloud, scalability is not an issue. Along with this, cloud-native data formats like GeoParquet and PM Tiles allow us to stream bits of geospatial data without having to download the entire data sets. Also, WebAssembly is allowing us to have near-native performance of spatial analysis right in the browser by using in-process databases like DuckDB, which has a geospatial engine built into it. Now, as I was researching what non-GIS users would need to use geospatial analysis, there were some obvious and key trends that I saw. One of the main requirements is that these GIS systems need to have zero or minimal installed to get started. Also, these systems need to run everywhere, irrespective of their operating system and device type. Also, many times geospatial data has PII or sensitive data in it, so users want strong data privacy controls. Also, users want consistent user experience. Many times you'll come across some of these lightweight tools which are easy to get started, but when you want to do some advanced analysis, then you have to switch to a completely new software. Also, users want to create these systems to be able to create and preserve data provenance because they want to share not only the source data and the end result, but also the analytical steps in between. Also, they want these systems to create geospatial workflows that are easy to understand and help them develop and improve their geospatial thinking skills and not just create pretty maps. I wanted to share this wonderful quote from the US Geospatial Intelligence Foundation. It says, "For the foreseeable future, expert tools wielded by analysts who lack critical thinking skills will result in nonsense making." Today, we have AI tools that literally give us answers in seconds. So now it is more important than ever before to make sure that we are asking the right questions to the right data. And the art of asking the right questions comes by building these critical thinking skills. A few GIS analysts will not be able to ask all the right questions. And that is by enabling data analysts from diverse backgrounds to be able to use geospatial analysis, will be better able to solve the problems in and around our communities. So I'm going to show you a demo here. Can we switch to that? So this is a web app. I preloaded 3 data sets. One is the subway stations, census blocks, and homicide incident locations. The idea here is that I got a job. The scenario is that I got a job, and I'm moving to New York City. And I want to find an apartment within half-a-mile radius of subway stations so that I can commute to work. So what we are going to do here is find all the census blocks within half-a-mile radius of these subway stations. And then I want to classify these census blocks into safe, unsafe, and dangerous categories based on the number of incidents of homicides in those census blocks. On the right side here, you'll see we have 4 categories of blocks: logic, aggregation, spatial, and data viz. And in data viz, I just have 1 map block for now, which basically creates a choropleth map. A choropleth map is just a colored map based on a value of a variable. Also, here you'll see there are different user levels. The idea here is that based on the user level, you will load the appropriate blocks. So for more advanced users, you would load more advanced blocks. So the first step is to create these half a mile radius around every subway station. So we can come here and select this block. Let's type in 0.5 miles. So basically it says create a circular zone of 0.5 miles around these subway stations. Now the technical term in GIS for this is called buffer. So what I'm trying to do is avoiding all the technical jargon and trying to use as plain words as possible. So let's execute this. So let's call it station zones. So you see it created this output here as step 1. And in the background, it generates the spatial SQL, and it executes that spatial SQL using the DuckDB as the spatial engine. And you can preview that output here. You see these are all the half a mile radius circles around every subway station there. So the next step is to find all the census blocks that are within these circular zones. So we can select this block here. And we can say find unique census blocks that share any common space with the station zones that we created in the previous step. Again, trying to use very simple words. And basically what this does is it finds all the census blocks that are completely within that circular zones that we created, or if they are partially within it. So let's run this. Let's call these zone blocks. Again, it creates the step number 2 here, and again, it generates the spatial SQL and executes it behind the scenes. So the third step now is to find the census blocks that are within those. The third step is to find the homicide incidents that are within those census blocks that were within that circular zones. So we can use this same block here and select homicides that are completely within the zone blocks here. And then we can execute this. Let's call it zone blocks homicides. So it added a third step. So you see how users can slowly build their workflow in small chunks, which I think makes it easier and manageable to use. Now, in the interest of time, I'm not going to go through all the steps, but I'll show you the end result. Now, let's assume that I completed my analysis, and I want to share this analysis with my colleagues. So what you can do here is click on this, and it creates a JSON configuration file, which has all the information packed into it to be able to recreate this analysis. And I wanted to show you that JSON file. So here is that JSON file. Now you can see there are 7 steps in it, out of which we completed the first 3 steps. And each step has all the information built into it. It has the parameters required for that step. It has the spatial SQL. And it also has the serialized Blockly workspace to recreate that block. Also, you'll see that there are the data sources, the 3 data sources that I preloaded, and it has that URL for that data set. So coming back here, assuming that I shared that JSON file with my colleagues can come to the same website here, and they can load the workflow, that JSON file. And it's going to recreate the analysis exactly the same way that I did. So you see it added those 3 data sources, and also it created the whole workflow with all the 7 steps. Now my colleagues can view it each step at a time. They can look at all the parameters, the SQL, the actual block, and also the output of that particular block. Also, they can see the whole block view of it. So if you click preview, it will show you every step at a time with each block and all the parameters. And if you go down here, you'll see the criteria that I used for classifying the census blocks into safe, unsafe, and dangerous. And also the colors that I assigned to those categories for creating the choropleth map. And what I feel is that by hiding all the details of the code and just showing this block view, I think users will be able to better focus on the semantics of the workflow rather than trying to struggle with the code behind the scenes. Also, now my colleagues can save this workflow as a data set, and they can then use this data set as an input to their workflow. So you can see how by easily exchanging our analysis with each other, we can build on each other's work rather than recreating everything from scratch. I have a bigger idea, which is quite exciting but very challenging, especially for geospatial, and that is the idea of using the agentic AI framework. If you imagine each step as an agent, each agent can encapsulate a specific type of logic, and imagine an AI manager that is trained on all these blocks, and it is trained on some curated data sets, and also it's trained on all these workflows that the users create, because ultimately it's a JSON file. Now, after being trained, this AI manager can then parse a geospatial question and then assemble these AI agents and orchestrate a workflow using these agents, and then execute them either in parallel or in sequence, depending on what is required for that workflow. And I'm hoping that will make this application even more intuitive and easier to use, and that will encourage more non-GIS users to start using geospatial analysis in their work. That's my time. I'm Kiran Batchu. Thank you for having me.